Hi everyone, welcome back to the channel. In today's video, we are going to talk about something that every CFD users encounter, but many beginners find confusing. Residuals. Whenever you run a CFD simulation, the solver reports residual values for continuity, momentum, energy, and turbulence equations. But what do these numbers really mean? Why do they drop as the solution converges? And most importantly, how do you know when your solution is accurate enough to trust? In this tutorial, we are going to discuss what the residuals are, residual importance in CFD, representative residuals in CFD, normalization and scaling, residuals scaling importance, residuals in ANSYS Fluent, and factors affecting residuals. By the end, you will have a clearer understanding of residuals and how to use them as a tool to judge convergence in your CFD projects. So, let's get started. What are residuals? Well, simply speaking, residuals are the errors that appear in our calculations after each iteration. Numerical solvers use iterative methods to solve a body of equations. It means they repeat the same process again and again and again to reach the correct answer. But if we want to be precise, the difference between left-hand side of equations and right-hand side of equations are residuals. And the smaller residuals indicate better convergence. Convergence is achieved when we say enough to our solver. No need to proceed anymore. We have the answers with the accuracy we are looking for. And that's when the residuals difference is negligible. But remember, there's always a difference between numerical solution and exact solution. They will never overlap entirely. Let's look at a simple mathematical example. We have three equations and three variables, x, y, z. Now, we want to solve these equations numerically. It is possible to have an analytical answer for them, but for the sake of this video, we are going to solve them numerically. Well, we are using an iterative method, so we make an initial guess, 0 for all variables. We input them into the equations, and we calculate our residuals. Subtracting right-hand side of the equation from left-hand side. Well, with our initial guess, we have pretty large residuals. So our answer, our initial guess, is not close to the exact solution. We need to iterate. So we update our variables, then again, input them into the equations and calculate residuals. The residuals are smaller this time. We are getting close. Again, updating our variables and calculating our residuals. Well, this time our residuals are pretty small, right? Especially for the third one. So we say we have achieved convergence. Now, this is our final answer. We have our answers. Now, let's compare them with the exact answers. Well, you see, for Z, the difference is very small. So we can accept it as converged. But I personally believe that x and y need more iterations. The difference between exact solution and numerical solution is kind of large still. And the fact that z converged sooner than x and y is completely normal. Some variables converge sooner than the others. Now, it's time to take our lesson to another level. Let's look at a CFD example. We want to study heat flux in a wall. Well, our wall has 3 boundaries: 100 degrees, 50 degrees, and 300 degrees from bottom. Now, let's write the energy conservation equation for cell number 1. The summation of energy inlet plus generated energy equals 0. Now, we want to assume that there is no generation of heat, so it's 0. So it says that the summation of inlet energy equals to 0. It means the energy that comes from left, right, down, up. And for our heat flux, we have Fourier's law, minus Ka delta T by delta X. Now, if we input Fourier's law into the conservation energy for cell number 1, we have an equation. Our final equation is the summation, an algebraic equation, summation of temperatures with coefficients equals a constant. Now, we can do the same process for all the other cells in our mesh. So at the end, we will have 4 temperatures, 4 unknown temperatures, and 4 equations. And all these equations have their own coefficients and their constant. We can write this body of equations into a matrix, a coefficient matrix, a temperature vector, and a constant vector. Simply saying, AT equals C. Now, when we solve this case numerically, here we have after 7 iterations. As you can see from our initial guess, as we go down, the difference between temperatures decrease. See? I mean, look at the last 2 rows, 6 and 7. They are pretty close. And even if you look at the plot, you can see after iteration 2, iteration 2, all of them are converged. And as I said, some variables converge sooner than others. Which variable converged here sooner? T4. So when we compare these answers, our final answers, with the exact value of the temperatures, we can see that convergence is truly achieved. And the difference between exact solution and numerical solution is negligible. So, why is there a difference between exact solution and numerical solution? from one point of view, all solvers have finite decimal places, finite precision. So it makes it impossible for the solver to calculate the exact number we are looking for all the time for all cases. But physically speaking, the difference is caused by energy imbalances. What is energy imbalance? Do you remember the conservation of energy, where we said that the total inlet of energy plus generated energy equals 0, and we assume there is no generation of heat, so our total heat flux equals 0? Well, news to you guys. In numerical solution, the total heat flux is not 0. Why? Let's take a look at our mesh once more. So our cell is surrounded by 4 more cells. And when we write the conservation of energy for this cell, as you can see, we have the difference of centroids. So if we knew the exact value of these nodes, their temperature, the equation would be equal to 0. But we don't know. Yes, we are using a numerical solution. We are using iteration. We are using initial guess. So it causes difference between temperature gradients among the walls. So the heat flux from west will not be equal to the heat flux from east. And same goes for north and south. So our equation will not be equal to 0. Now, but we need our equation to be equal to 0. Why? Well, we want our solution to be both physically and mathematically correct. So to satisfy the conservation of energy, we add a new term into our equation. This term is called residuals, and it stands for the energy lost or gained in each cell. So the equation was not equal to 0. We added a new term and we made it 0. Do you remember the definition of residuals at the beginning of the video? I said the difference between right-hand side of the equation and left-hand side of the equation, right? That's it. Our residuals are our energy imbalances. Now, that was just for one cell. You can do the same for all cells in your mesh. And you will have a matrix for it. You have a coefficient matrix, a temperature vector, a constant vector, and residual vectors. And the smaller the residual vector, the more accurate your answers. Now, here we are using the energy equation, AT minus C equals R, right? But you can use this form for all governing equations, for continuity, for momentum, for turbulence equations. So the universal form is A phi minus C equals R. Now, let's take a look at 2 plots of residuals. So, ideally, what is happening in the plots on the left is what we are looking for. The residuals decrease, 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 and then they pass the threshold, and the variation in residuals are negligible. And here we are monitoring continuity, x momentum, y momentum, energy, and k epsilon. Now, this is an ideal plot, okay? A more real one has noises. This is more realistic. Now, this is what we are looking for, but sometimes we can get this. As you can see, they diverge. Our iteration as goes forward, our residuals get bigger, bigger, and bigger, which is bad, okay? That's not what we are looking for. And it shows that you need to change if you're using a commercial software such as Fluent, your setups or your mesh. It could be any reason why your case diverges. Another thing that can happen for your residuals is that they fluctuate. It's not diverging. It's not converging either. So again, it could be due to your mesh or your setups. You have to check your equations from the beginning, your setups, to find the problem. Now, if you have noticed, for the y-axis, for the residuals, it's logarithmic. Do you know why? Because the exact value of residuals are not important to us, but the order of magnitude of residuals matters to us. A question may come up to your mind. My mesh has 10 million cells. Should I monitor all 10 million residuals? Of course not. It's tiresome and impractical. What you need to do is to use representative residual. As its name says, it stands for all the residuals in your mesh in that iteration. There are 3 common methods which CFD solvers use to calculate representative residual. We have the L1 norm, that is the average of absolute values of all residuals. We have L2 norm, that is the square root of the average of the square of all residuals. And we have the L infinity norm, that is choosing the largest and maximum residual. As you notice, you find that L1 norm and L2 norm are divided by the number of cells. It is because we like to remove the effect of number of cells on the value of representative residual. And since L2 norm uses the square value of residuals, larger residuals add more weighting to the representative residual, while all residuals have equal weighting in L1 norm. Now, let's look at an example. We have these raw residuals. Now, we want to calculate representative residual using these 3 methods. As you can see, using different method gives us different value for representative residual, and they are all correct. You have raw residuals, you have their values. Can you judge whether your solution is converged or not? I mean, do you look at the residuals and see, well, these residuals are pretty small, so my solution is converged? Or to answer this question, Let's look at two cases. On the left, we have the heat flux of one cell. It shows that on the west wall, we have the heat flux of 0.1 watt per meter square, and on the east wall, we have 0.09 watt per meter square. Now, in the case on right, the west wall has the heat flux of 1 watt per meter square, and the east wall has 0.99 watt per meter square. As you calculate residuals for both cases, you see that the residuals are equal to 0.01 watt per meter square. So, are they both cases converged? Now we see we cannot decide. So, what's the solution? The solution is scaling residuals. When you scale residuals, you can see what percent of error you have. And you need more iterations or your solution is converged. As you can see, in the case on right, we have 1% error, while for the case on left, we have 10% error. It means we need more iterations. Scaled residuals shows the percentage of gained or lost energy in our cell. And to calculate scaled residuals, we need to divide residuals by a scaling factor. This scaling factor could be mass flow rate at inlet for continuity. For momentum, it could be momentum flux at inlet. For energy, it could be the energy flux at inlet, and so on. Just one thing that you need to know is that for continuity, it's not always scaling. Sometimes it's normalizing. Why? Well, for example, cavity. In a cavity, there is no inlet. You don't have mass flow rate. And the one you have in the cells, you don't know. You need your solution to be converged first, and then you can have the value of mass flow rate. So, instead of scaling, you need normalizing. How do we normalize? Well, pretty easy. We divide the residuals by the maximum residual in the first 5 iterations. So it's like max to residual. Why first 5? Because maybe your residual plot is like this. If you choose first iteration, you are choosing wrong value for normalizing. And it mislead you. You may think that, okay, it's converged or behave differently. So we choose the first 5, the maximum of first 5. Why not just choosing the maximum? Well, because if your solution diverge, your maximum value keeps increasing and you will not have a correct normalization. Now, why scaling is necessary? First, it can give us the scale we are looking for to judge whether our solution is converged or not. Our values are comparable when they are scaled. And sometimes, if we do not scale, small values can mislead us to thinking that we achieved convergence, and large values also in a small system can mislead us to wrongly thinking that we have achieved convergence. Okay, that's it for residuals. And if you liked today's video, don't forget to comment, subscribe, and hit the notification bell. We'd also like to hear from you, so please leave a comment in the below. And if you'd like to connect with us directly, you can find all our links, including website address and social media, at the description box. Feel free to reach out anytime. Thanks for watching. See you in the next video.